Hello everyone. Today we are going to see an important chapter of your competitive examinations for JEE Main. Welcome to the crash course of some basic concepts of chemistry, which is the backbone of physical chemistry and your JEE Main and Advanced and NEET preparation. This chapter isn't just important for the exam where it fits you easily 4 to 8 marks in your exam, but it also builds the foundation for solving tricky problems in advanced topics like equilibrium, thermodynamics, and much more. We'll tackle the concepts like mole concept, stoichiometry, and concentration terms while practicing side by side to make sure you master them. Trust me, once you get this right, the rest of the chemistry becomes lot easier for you. So grab your notebook, stay focused, and let's dive in together to ace this chapter and boost your confidence for JEE. First of all, this chapter starts with the basic terminologies like elements, compounds, atoms, molecules, atomic weight, molecular weight, and blah 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 blah. Since this is a crash course, I'm not going to concentrate much about the basic terminologies because I know you already mastered in that. So let's start with the important topics, which is relative atomic mass. Before that, I would like to just brush up the concept of molecular weight. What is molecular weight? What is molecular weight? It's the weight of a molecule. Is it? Yes, somewhat that is right. It is an actual mass of one molecule by 1/12 of the mass of one atom of carbon-12. But we are not using that formula to find out the molecular weight. We are just summing all the weights of the atom present in the molecule to find it out. For example, NaCl. The weight of sodium is 23 and weight of chloride, that is 35.5. In total, it becomes 58.5. We find out the molecular weight like this, right? As simple as that. Similarly, for H2O, it will become 18, and ammonia, that will become 17, and etc. But examiner won't ask you this kind of small questions or silly questions to ace the exam, right? So let's go deeper. We know about atomicity. They may ask you questions in atomicity if he or she, the examiner, is very kind-hearted person. But I don't think so. But atomicity is the number of atoms present in a molecule. Atomicity of H2O, that is 3, and atomicity of oxygen molecule is 2. Atomicity of H2SO4 is H2SO4 is, yes, that is 7. Let's dive into the most important part, that is mole concept. What is mole? Mole is the amount of substance that contains as many entities. I mentioned that as an entity. Amount of substance that contains as many entity. I'm not mentioning simply atom. I'm not mentioning simply molecule. I'm not mentioning simply pencils or apples or anything. Whatever the entity, whatever you are taking for considering 1 mole, that is equal to that. More importantly, we use 1 mole is equal to Avogadro number or Avogadro's constant, also referred as Na, not sodium, which is 6.023, sometimes 22, into 10 to the power 23 entities. If I'm considering 1 mole of apple, then that is equal to 6.023 into 10 to the power 23 apples. Okay, so don't get confused with what does this number refers to. It refers to whatever you are taking. Okay, let's move on to gram atomic mass or gram molecular mass. What is this? When a numerical value of an atomic mass of an element is expressed in grams, then the value becomes gram atomic mass. In simple words, gram atomic mass is equal to mass of 1 gram atom. Okay, if we are representing that in grams, then that will become gram atomic mass. Say for example, what is the gram atomic mass of oxygen? Gram atomic mass of oxygen. Mass of 1 gram atom of oxygen, that equals to GAM of oxygen, which is equal to mass of 1 mole atom of oxygen, which is nothing but 16 by 1 mole to die. So that is Na, Avogadro's constant. Mass gram into Na, which becomes 16 gram. What I can say you is that atomic mass, if that is referred in grams, then that will be gram atomic mass. In simple words, in most of the conditions. Similarly, gram molecular mass is mass of 1 gram molecule. Again, mass of 1 mole molecule and etc. For example, if I am considering GMM, gram molecular mass of H2SO4 means, then the mass, which will become 98 divided by Na in grams, so which will become 98 grams. Okay, so I'm just giving you the formula for whatever we have referred till now, which is mole of atoms one mole, which we can find it out by weight by molecular weight or molar mass. Mole of molecules weight by gram molecular weight. Mole of atoms, which is equal to atomicity into mole molecules, what we got in the second formula. Right? Similarly, if I'm considering that as a gas, then we will be referring that to volume, isn't it? So mole of gas which is equal to given volume divided by 22.4. Here you have to be careful whether you are finding it out on which condition, STP condition or RTP condition. It will get varied. The number will get varied for different conditions. Here I am mentioning it for the most common condition of STP. So number of particles, how will you find? The mole particles, which is equal to number of particles divided by Na, which is Avogadro's constant. Let's solve one problem to sum up what we have learned till now. The problem is that calculate the number of molecules and atoms present in 2 grams of nitrogen. So number of moles, which is equal to mass by molecular mass, weight by molecular weight. So here I have 2 divided by molecular weight of N2 will become 28. So it's 1 by 14. And number of molecules which is in a given mole, like what we have found out as a mole, which is equal to 1 by 14 into Na one molecule of N2 gas contains how many atoms? 2 atoms. So number of atoms which is equal to 2 into Na by 14, which is again Na by 7. So these many atoms present in 2 grams of nitrogen. This relative density then. Relative, which is just a comparison, right? So comparing gas A with gas B. So density of A, mean the gas A, divided by density of gas B. These are the important formulas to be remembered in this concept. For specific gravity, density of solution by density of water. So we are comparing the density of the given solution with density of water. Say for example, this is very vague. You are just giving the formulas. How to apply it? So for example, let's say I'm taking again a nitrogen gas, okay, which is having a vapor density. Nitrogen gas that is having the vapor density of 70. Okay, so we don't know that is having nitrogen, but I don't know this X. So using this vapor density, how will you find the X? Here comes the one more formula. the most important formula, that is molecular weight of the gas, which is equal to 2 into vapor density, just 2. So 2 into vapor density, they have given us 70, so which is equal to 140. So one nitrogen, the one molecule of nitrogen, the molecular weight is 28. Here I am having 140, which means what is X? So total I am having 140, which is the X will be 5, isn't it? So this kind of question can be asked in your examination. Now let's move on to the integral part of this chapter, that is percentage formula, empirical formula and molecular formula. How the questions can be asked in this part. Here you have to remember one simple formula, that is percentage mass, which is equal to number of atoms into atomic mass divided by molecular mass. Since they are asking in percentage, put into 100. Okay, so number of mass, atomic mass divided by molecular mass. That is for finding out the percentage mass or percentage formula. What about empirical formula? What is empirical formula? It is like a nickname of the molecular formula. It can be common for many compounds, right? So we'll talk about the empirical formula while solving the problem. For now, I'm skipping this. I'm going to molecular formula and empirical formula relationship. How it is connected? What is the relation between these two is that it is connected by one single number, that is n. So the n times the mass of the empirical formula and the molecular formula mass, which is connected by the factor or connected by the number n. That n is equal to the ratio of molecular formula by the mass of empirical formula. How we can say like that? What kind of question can be asked from this part? Let's say I'm having a compound where it is having carbon. Percentage of carbon is 52.2%, and I'm having hydrogen. %, and I'm having oxygen, which is 34.8%. Okay, so I'm having carbon, hydrogen and oxygen are present in a compound. I don't know how many atoms are present. I have to find it out. And the molecular mass of the compound is 92. Okay, I have to find the molecular formula of the compound. So let's find it out step by step. First, you have to write the percentage of the elements given. Then write the mass or atomic weight of the element. Carbon atomic weight is 12, hydrogen 1, oxygen 16. Now apply the simple formula, percentage weight by atomic weight. So here you can see 52.2 divided by 12, 13 by 1, 34.8 divided by 16. So what are the quotient I'm getting? I'm getting around 12, 12 4s are 48, so I'll get around 4. More accurately, I'll be getting 4.4. So here I'm getting 13, and once again I'll get 2 around, so 2.2. Now I have to take a simplest ratio of these numbers. Here I'm having 4, here I'm having 13, and here I'm having 2. The simplest ratio would be dividing the smallest number with all of these. For example, 4 by 4.4 divided by 2.2, which is equal to 2. 13 by 2.2, which is equal to 5.9, and 2.2 divided by 2.2, which is equal to 1. So take a round figure of the simplest ratio, which will become carbon is 2, hydrogen will become 6 because I'm having 5.9, oxygen is 1. So this is an empirical formula. It's not a molecular formula. It is the simplest ratio of the elements we are getting. Now we are going to find the molecular formula out of this. How? As I said, it is a difference of air. So find out the empirical formula mass. Which is equal to 12 for carbon plus 1 for hydrogen, 16 for oxygen. So in total 24 plus 6, 30, 30 plus 16, which will be 46. Empirical formula mass is 46 and the molecular formula mass is given as 92. So N is equal to molecular formula by empirical formula mass, right? So 92 by 46, which I am getting 2. N is equal to 2, which means that molecular formula equal to 2 into empirical formula, which is 2 into C2H6O, that is C4H12O2. Okay, this kind of question can be asked in your test because this is having the probability of very high. Okay, let's delve into the next part of the chapter, which is the balancing part. So hope you already know about how to balance the reaction, how to calculate the limiting reagent, which is excess reagent, and how to know about which limits are where to calculate the product amount, right? So let's solve one problem based out of this. That is, because by solving problem we can revise the concept because we are having very less time. So for complete combustion of 3 gram of ethane, find required moles of O2 and formed moles of CO2. Also find volume of O2 and CO2 at STP condition, standard temperature pressure. Okay, what is combustion reaction? Combustion is combusting of hydrocarbons to give carbon dioxide and water, right? Heating, very high temperature heating. So the reaction will be for ethane, C2H6 plus O2, that is undergoing the reaction to form CO2 plus H2O. I'm leaving it to you to balance this reaction because we don't have much time to cover all these concepts in the crash course. And you can also get the shortcut to do this combustion reaction, right? So I'll attach it with the document, the shortcut method. So the balanced part of this reaction is 2C2H6 plus 7O2 gives 4CO2 plus 6H2O. Now, what are the things we need to find? Find the required moles of O2 and formed CO2. The total amount of ethane given is that 3 grams. So number of mole. The 3 gram is equal to 3 by 30. What is 30 here? The molecular weight of ethane, which will become 1 by 10. It's 0.1 mole, isn't it? So required moles of O2. The number of moles of O2 taken is 0.1 mole. So the required amount of O2 will be required mole of O2, which is equal to, it is in 2:7 ratio. 2 moles means 7 moles will be required. Here I am having 0.1 mole. Then that would be 0.35. How? You can do unit conversions or cross multiplication. 7 for 2. 2 for 7. How would become 0.1 for x? So 0.1 into 7 divided by 2, which will become 3.5 into 0.1, then that is 0.35 moles. Don't rely on the formulas, don't do the formulas each and every time. You should know these conversions also. And volume of O2, which will become at STP, which is just multiply with 22.4, isn't it? So 0.35 into 22.4. Then I'll be getting it as 7.84 liters. That is for oxygen. What about carbon dioxide? What is the ratio of oxygen involved or ethane involved with carbon dioxide? That is 2 moles for ethane, 4 moles of carbon dioxide is produced, right? So 2:4 ratio. If I'm having 0.1 mole, then that would be 2 for 4. 0.1 is for 0.2. So produced moles of CO2, which is 0.2. Volume, which is again multiply it by 22.4, which is 4.48 liters, right? So we have found out the mole and the combustion reaction, balancing everything in one single question. Let's move on to another interesting and important part of this chapter, that is limiting reagent and excess reagent. What is limiting reagent? Which will get consumed first? That is called limiting reagent, which means that if you're having 2 idlis and 2 packet of sambar, if you want 2 packet of sambar for 1 idli, then sambar will get finished first. 1 idli will be remaining, so that is excess. Sambar is limiting reagent and the excess reagent is idli. Okay, so which will get consumed first is limiting reagent, which is excess or extra, that is excess reagent. Here, 10 types of questions can be asked. The first type involves mass-mass relationship. So what is mass-mass relationship? As I already told you about what is balanced reaction, what is limiting reaction and everything. So let's solve each type of problems so that we'll get an idea how to solve a question. The question is that what is the amount of silver chloride Let's solve each problems so we'll get an idea how to tackle this kind of question. The type 1 is mass to mass relationship. So for this, I would like to take you a simple example but effective one. How much iron can be theoretically obtained in the reduction of. This type of question may give you the concept of formation of the product. Okay, so make sure that you remember the reaction of simple concepts. For example, here we are talking about 1 kilogram of ferric oxide. The reduction of ferric oxide we are talking about. So how that will happen? So reduction means obviously hydrogen. So Fe2O3 plus hydrogen to give Fe and H2O, right? So iron gained 3 electrons to form Fe0. How to balance this reaction? Once again, if you want the short trick or how to do the redox reaction balancing very easily, let me know. We'll do that in separate video. Okay, so Fe2O3 plus 3H2 gives 2Fe plus 3H2O. Now it is completely balanced. What was the amount given in the question? That is 1 kilogram. So 1 kilogram means how many moles? N will be weight by molecular weight. So I'm taking it in grams. 1000. So unit conversion is very important, guys. Don't forget that. So 1000 grams divided by 160, which is the molecular weight of iron oxide, ferric oxide. Okay, so I'll be getting mostly 100 by 16 moles. Okay, from the equation, from the reaction coefficient, what you can find it out is that 2 mole of iron are obtained from 1 mole of ferric oxide, which is in 1:2 ratio. 1 mole of ferric oxide is reacting means 2 mole of iron I'm getting. Right? So the number of moles of iron can be obtained, that is into 2. Right? So this is number of moles of ferric oxide. This is number of moles of iron. So 1:2 ratio. So 2 into 100 by 16, which will become again 100 by 8 moles. So they're asking how much. How much means they're asking in terms of grams. So then check out your options also, whether they are asking it in grams or kilograms. Then answer it accordingly. Okay. So here let me assume that they are asking it in grams. So 100 by 8 mole. So which is equal to how many grams? Let me simplify it so that it will become 12.5 mole. So number of mole is equal to weight by molecular weight. Weight is equal to number of moles into molecular weight. Molecular weight of iron, because we are going to calculate that only, right? So 12.5 into molecular weight of iron is 56. So it will become 700 grams, or else it will become 0.7 kilogram. So either way you must be able to answer it. Okay, this is mass to mass relationship. The type 2 is that mass to volume relationship. We already solved this type of question. Just now we have solved the question about ethane, right? Combustion of ethane. Here you can see they are asking it with mass with the volume of gas produced upon the combustion of the solid, mass of ethane, right? So this is mass to volume relationship. Okay, what about the next category? The next one, which can be asked in the way to get NTP conditions in a container. I'm having 100 ml of N2, and third type of question I'm telling you, 100 ml of N2 and 100 ml of H2. What is produced? Ammonia is produced. N2 plus H2, Haber's process. Right? Mixed together to form ammonia. What is the question? The question is that how much volume of ammonia produced? There is also similar kind, the mass to volume. This kind of question can also be asked. So here you have to find out which limits the reaction. The reaction is N2 plus H2 gives, I'm just taking the forward direction only, NH3, the balanced form, which is 2H2 gives 3H2 gives 2NH3. Okay, so here I have 100 ml of N2 and 100 ml of H2. Now we have to find it out which limits the reaction. How we can do that? How we can find out which limits the reaction? One way is that you can find the number of moles from the given volume and then calculate it with the ratio to find the resultant moles. Or else the simplest way is that here I know the stoichiometric coefficient 1, 3, 2, right? So I have to divide the given volume by the stoichiometric coefficient. For example, 100 by 1, here 100 by 3. Which will give you the least number? Here I am getting 100, here I am getting 33.3. Then that will be taken as, that should be taken as limiting reagent, because it will get consumed first to give the product. It stops the reaction. Okay, so it is the limiting reagent. So once we found out the limiting reagent, the next step is find the product, find the volume of the product. So the reaction is depend on hydrogen consumptions, right? So 3:2 ratio. 3 moles of hydrogen for 2 moles of ammonia. So where I can take 3 ml of hydrogen to produce 2 ml of ammonia, right? So let me take it in this way. For 100 ml of H2 is producing how many amount of ammonia, right? Producing ammonia, which is equal to, where that is in 3:2 ratio. Here I am having 100. So 100 into 2 divided by 3, which will become 200 divided by 3. Then that is 66.6 ml of ammonia has been produced. Okay, so this kind of question can be asked. And after that, just go a glimpse of law of combination, chemical combination, what is law of conservation of mass, law of multiple proportions, Avogadro law, Gay-Lussac's law, and definite proportion. Everything just go through it. They won't ask much question about this directly related to the law, but you must know about the law. Okay, so let's move on to the next part that is relevant to redox. We are going to put in separate video for redox reactions, but I'm just going to give you the glimpse of the terminologies which is related to mole concept, that is equivalent weight. equivalent weight, which is equal to atomic weight divided by valency factor. So if they are asking for the equivalent weight of ions, then atomic weight of that ion divided by its valency. Okay. How to find the equivalent weight? That comes under the redox part. How many electrons are lost, how many double decomposition method, metal to metal displacement method, and everything. We'll do that in redox part. Now I'm jumping to the next part, that is stoichiometry and concentration terms. What is concentration term? How that would be related? What is concentration? First of all, it is something related to the strength of the solution. How many ions are present? What makes it so strong? Right. So if there is a solution which is having 50 ions in 100 ml, and if I'm comparing that with the 100 ions in 100 ml, the second solution is much more stronger, much more concentrated than the first one, right? So it tells about the strength of the solution. So how we can define it? Do we have any units? Do we have any formulas? Yes, we do. So for concentration terms, we have the basic formulas of molarity. Please make sure that you are following the units, which is very, very important to note it down. Molarity, which is represented by capital M. Okay, so which is number of moles of solute divided by volume of solution. In which unit? In liters. If you are taking it in milliliters, then you have to multiply it into 1000. Okay. Here I am taking just in liters. So second term, that is molarity. Molarity, which is denoted by small m, which means that number of moles of solute divided by weight of solvent. Weight of solvent, which is in kilogram. Okay, if you are taking it in grams, then you have to multiply it into 1000. Then another important term, why I told about the equivalent weight, is that for normality. So normality is represented by N, capital N. Don't get confused with normality with number of moles. Number of moles is in small n, normality which is in capital N. Okay, so normality, which is equal to mass of solute, which is in grams, divided by equivalent mass into volume of solution. Volume of solution. Okay, only in case of molarity we are taking it the solvent, and that is in weight. Okay, in other terms we are taking volume in liters of the solution, whole solution. Okay, And what is the relationship between molarity and molality? What is the difference between these two? These two are dealing with, the former one, molarity, is dealing with the volume of solution. The later one, molarity, is dealing with weight of the solvent. Okay, please make sure that you are not doing mistake over there. And the last term, that is mole fraction. Mole fraction is that the percentage or the fraction of amount of components present in the given compound. Okay, let's say 25% or 1/4 of carbon is present in CH3. 3/4 of hydrogen is present in CH3. In total, how many parts is present over there? Right? So if you are adding those mole fraction of every element in a compound, you should get 1. Okay, so that be careful with that. So the mole fraction of, let's say, of A, which is equal to moles of solute A divided by moles of solute A plus moles of solvent B. Okay. Similarly, if you are writing it for chi B, then that is moles of solvent B divided by the same thing, moles of solute A plus moles of solvent B. Okay, so upon addition of chi A and chi B, we should get 1. It can be of chi C, chi D also. Okay, upon addition of all those fractions, you should get 1. So the options are 0.6 molar, 0.7 molar, 0.8 molar, and finally 0.9 molar. Okay, so they have given the molecules of urea dissolved in 1 liter of water. We don't have the number of moles, we just have the molecules. And we have to find out the molarity if that is undergoing dimerization. 40% of urea is undergoing dimerization. So initial moles, initial molecule, that is 6.02 into 10 to the power 23, which is nothing but 1 mole of molecules, right? So it is undergoing 40% of dimerization. 40% molecules are undergoing dimerization. So 40% from this is how much? So 40% of urea undergoing dimerization. So molecules dimerized is how much? So 40%, I'm taking it as 0.4. So dimerized molecule, which is 0.4 into 10 to the power 23. So the remaining molecules will be 0.6, isn't it? So upon adding it, you will get 100. Here, point to be noted is that upon dimerization, what happened? It is forming one single molecule with 2 urea content, right? So I have to divide it by 2. For the molecule whatever got dimerized, I have to divided by 2 to get the number of molecules are being formed. So the total molecule after dimerization 6 Na, I'm just taking it as Na, plus 0.4 divided by 2, that is 0.2 Na. So total 0.8 Na, right? So the molarity, what we have to find is that number of moles of solute by 1 liter volume of the solution, that is in liters. 1 liter they have given. So 0.8 moles of molecules present over there. Moles of molecules. So I am cutting out this Na because I'm just taking out the number of moles. So 0.8 moles divided by 1 liter, which is equal to 0.8 mole. 0.8 molarity, 0.8 m. Okay, is it clear? Hope you have understood the concepts of some basic concepts of chemistry chapter. Do a lot more practice. I'll be attaching some set of questions with the solution so you can go through it. If you have any doubt, please do ask. We'll sort it out. All the best for your exam. Do it well. Practice more because practice makes a man perfect.